Dear students, I am Nilanjana Sanyal, an online math tutor from India. Welcome you all to my channel NS Online Math Classes. Our today's topic is the binomial expansions using the Pascal's triangle. We are doing the chapter on the binomial theorem, and it is a chapter which is included in the IGCSE Additional Mathematics, in AS level maths and in IB maths. Okay, so we have done the factorial notation part, and now we are coming to the binomial expansion using the Pascal's triangle. Okay, so without any further delay, let us start with our today's session, the binomial expansion and the Pascal's triangle. Now, what is the meaning of the binomial expansion and what is the meaning of the Pascal's triangle? Fine. So, binomial. What is a binomial? Sorry, this is a binomial. We know that if you have a single term, say it may be a constant 20, it may be a variable x, these are all monomials because you are having only a single term. If you have two terms, that is, say it can be x plus 20, it can be y plus x or x plus y, okay, it can be x minus y square. So these are all examples of binomial. Okay, these are the three examples of a binomial expression. Okay, so binomial expansion, these are all binomial expressions. So what do we mean by expansion? The expansion comes when we are having some power. The binomial expression is having some power. Say it is x plus 20 raised to the power of 5. We know a plus b raised to the power of 2. This is also a binomial. So a plus b when raised to the power of 2, we know the identity. It is a square plus 2ab plus b square. So this is the binomial expansion. A plus b is the binomial. We require this expansion part because of this power of 2. And this is a plus b times a plus b. If we multiply a plus b times a plus b, we get a square plus 2ab plus b square. Okay, so first of all, we have known what is a binomial, and then we have known why is this expansion part coming into picture. Why is this expansion needed? The expansion of a binomial expression is needed when that binomial expression is raised to some power. Okay. Now coming to the Pascal's triangle, the significance of this triangle. First of all, before going to the Pascal's triangle, let me say what are the coefficients of these three terms. A square plus 2ab plus b square. Obviously, the coefficient of a square is 1. The coefficient of ab is 2. This is 1, this is 2. And the coefficient of b square is 1. Okay. So, these are the three coefficients of the three terms of this binomial expansion. And these coefficients are obtained from the Pascal's triangle, named after the mathematician Blaise Pascal. Now, the Pascal's triangles, sometimes you see the Pascal's triangle is starting with this number 1 because a plus b raised to the power of 0 is equal to 1. But I am not taking this row because anything raised to the power of 0 is 1. So, I am just excluding this row because of this point that I have written. I'll be coming to those points later, but first of all, let me show you the Pascal's triangle. I am starting with this row 1 and 1. This corresponds to a plus b to the power of 1, which is equal to a plus b. Okay. The coefficient of a is 1, that is this. The coefficient of b is 1, that is this one. Okay. So a plus b raised to the power of 1 is 1 times a plus 1 times b, and these two are given by these two ones. And this is the row number 1. What is the row number 2? Always the Pascal's triangle will be starting with 1 and ending with 1. So the starting number is 1, and the middle one numbers will be obtained by adding the two numbers immediately above the row that we are now writing. So 1 plus 1 is 2, and then the ending number will be 1. For row 1, you see there are two numbers. That is, the row number will be having row number plus 1 number of terms or number of numbers. This is the row 2. This is the row 2. So it is 2 plus 1, and we are having 3 numbers in this row. So this corresponds to a plus b raised to the power of 2, which is equal to 1 times a square plus 2 times ab plus 1 times b square. See, 1, this 1. This is 2, and this is 1, this is 1. Okay. For row 3, it will be starting with 1, and then these two added, 1 plus 2 will be giving us 3. Again 2 plus 1 will be giving us 3, and then it stops at 1. Because it is R3, there will be 4 terms. 1, 3, 3, 1. This corresponds to a plus b to the power of 3. Okay. I am writing the expression, the expansion, but I will be showing you how am I coming up with these terms. I will be showing you the authenticity of these rows. A plus b whole square we all know, but maybe many students do not know the expansion of a plus b whole cube. So therefore, I will be showing this expansion. But first of all, let me write the terms. It will be 1a cube plus 3a square b plus 3ab square plus 1b cube. Okay. Next, if I come to say R4, what will that be equal to? Starting with 1, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and since it is R4, there will be 4 terms, so the last one will obviously be equal to 1. So this is a plus b whole to the power of 4. Okay. So again, let me write the expansion, and then I will be showing the authenticity. I will be proving that. Okay. So it is 1a to the power of 4 plus, this is 4. So 4a cube b plus 6 a square b square plus 4 ab cube plus 1 b to the power of 4. Okay. Now coming to the proving part. I start with a plus b whole to the power of 3. So a plus b whole to the power of 3 is equal to a plus b times a plus b whole square. And a plus b whole square, we know the expansion of a plus b whole square, which is equal to a square plus 2ab plus b square. Okay, and now we multiply. A times a square is a cube, which is 1 times a cube. A times 2ab is plus 2a square b, and a times b square is 1ab square. Okay. Next, b times a square is plus 1a square b plus b times 2ab is 2 plus 2ab square, and b times b square is plus 1b cube. Okay, so it is 1a cube, so it is 1a cube and plus 2a square b and plus 1a square b will be giving us plus 3a square b, plus 1ab square and plus 2ab square will be giving us plus 3ab square and plus 1b cube. So this, you see the expansion that I am getting by multiplying. Actual multiplication is the same as that I have got using the Pascal's triangle, the row 3 of the Pascal's triangle. Okay. I don't have actually much space, so it may appear to be a bit clumsy. I apologize for the same. Okay, but I hope that you are being able to understand. Okay, now let us come to the a plus b to the power of 4 part. Again, this is equal to a plus b times a plus b whole to the power of 3. So this is equal to a plus b times a cube plus 3a square b plus 3ab square plus b cube. Okay, so now again we will be multiplying. A times a cube is 1a to the power of 4. A times 3a square b is plus 3a cube b plus 3ab square is, a times plus 3ab square is 3a square b square, and a times b cube is plus 1ab cube. Again, b times a cube is plus 1a cube b. B times 3a square b is plus 3a square b square. B times 3ab square is plus 3ab cube. And finally, b times b cube is plus 1b to the power of 4. Okay. So, this is equal to 1a to the power of 4 plus, we have any 3a cube b, yeah, plus 3a cube b and plus 1a cube b. So, it is plus 4a cube b, 3a square b square, 3a square b square. So, plus 6a square b square plus ab cube plus 3ab cube plus 4ab cube and plus 1b to the power of 4. Now you see this expansion is exactly the same as we have got over here using the Pascal's triangle for the coefficients. I'm not talking about what the powers of A and B and all. Only for the coefficients. We use the Pascal's triangle only for the getting the coefficients of the different terms. Okay. So now I have shown the validity of the numbers that we get from the Pascal's triangle for the binomial expansion. I have shown for the row 3 and row 4, you can check for any row, you will be seeing the numbers are indeed the same. Okay. So now that we have known what is the Pascal's triangle and what is it used for, let us move back to the points that are given. So, for the expansion of a plus b whole to the power of n, we have seen up to a plus b whole to the power of 4, where n belongs to any natural numbers or n is a positive integer. Starting value of n is equal to 1. That is why I did not include this row in the Pascal's triangle, because I have said that n belongs to the set of natural numbers where the smallest value that n can have is 1. So I cannot include this row a plus b raised to the power of 0. Had I had written n belongs to the set of whole numbers, I could have included this. Okay. But since I have taken n belongs to the set of natural numbers or positive integers, I have started with this as the first row, which is 1 and 1, which is a plus b raised to the power of 1. Okay. So, what will be the expansion? The first point says the power of a. A is what? The first term of the binomial expression. The power of a in the first term is n. See, it is a plus b to the power of 1, that is n equal to 1. So, power of a in the first term is 1 and in the last term is 0, because it is b to a to the power of 0. A to the power of 0 is 1. Therefore, we do not write this a to the power of 0 explicitly in this term. Okay. So, the power of a in the first term, a is the first term of the binomial expression, and in the expansion, the power of a in the first term is n and in the last term is 0. Whereas the power of b is the second term of the binomial expression. So, power of b in the first term is 0 because you don't see any b over here, because it is b to the power of 0. So, b part is missing. Because the power of b in the first term is 0 and the last term is n, b to the power of 1. Similarly, for a plus b to the power of 2, since n is 2, power of a in the first term is 2 and power of a in the last term is a to the power of 0. And power of b in the first term is 0 and last term is 2. Okay. Same thing, power of a in the first term is 3 because n is equal to 3. And power of b in the last term is 3 because n is equal to 3. Okay. This is followed every time, no matter what is the value of n. Next point says, as we look from the left to right, as we move from the left to right, that is our usual way of reading things, across the expansion, the powers of a decrease by 1, while the powers of b increase by 1. See, for a plus b whole to the power of 1, first power of a is 1 and the last power of a is 0. It has decreased by 1. For a plus b whole to the power of 2, starting power of a is 2 and then it is 1 and finally it is 0. But in the case of b, the starting power is 0, then for this it is 1 and finally it is 2. For a plus b whole to the power of 3, the first term of first term is containing a power of 3 for a. Second term is 2 for a, third term is 1 for a, and the last term, the fourth term, is a to the power of 0. So the powers are getting decreased by 1 for a, the first term of the binomial expression. Whereas for the second term of the binomial expression, it starts with 0 and ends with n, and in every term the power gets increased by 1. Okay. Next point, the sum of the powers of a and b in each term of the expansion is n. If I take, say, let me choose another color. So, if I take this one, this is b to the power of 0. So, 1 plus 0 is 1, which is the value of n. For second term also 1 plus 0 is 1, which is the value of n. For a plus b to the power of 2, it is 1a square and b to the power of 0. 2 plus 0 is 2. This one is a to the power of 1, b to the power of 1. 1 plus 1 is 2. This is 2 plus 0, again 2. Over here you see a square b, so 2 plus 1 is 3. ab square, 1 plus 2 is 3. Okay. Every time the power of a and the power of b when added will be giving us the value of n for each term. Okay. And the number of terms in the expansion is n plus 1. When a plus b is getting raised to the power of 1, that is n is equal to 1, we have a plus b, 2 terms. When the power of a plus b is 2, that is n equal to 2, we have a square plus 2ab plus b square, 3 terms. When it is a plus b to the power of 3, that is n equal to 3, we have a cube plus 3a square b plus 3ab square plus b cube, 4 terms. For a plus b to the power of 4, we are having 5 terms. So, whatever is the value of n, the number of terms is 1 more the value of n. Okay. And finally, the coefficients of the terms are the rows of the Pascal's triangle that we have seen. The nth row of the Pascal's triangle gives the coefficients of the expansion a plus b to the power of n. We have checked that, we have done up to R4, and you can get other rows as well. You just keep on adding. First number will be 1 and the last number will be 1, and the in-between numbers will be obtained by adding the 2 numbers immediately above the number which we will be writing, and you add the 2 numbers from the previous row to get the final number. So this will be 5, this will be 10, this will be 10 again, this will be 5, and this is 10 actually. This will be the R5. So that way you just get the terms or the coefficients rather, or the different terms of the binomial expansion. Clear? So now that we have learnt about the rule of how do we expand, because if it is say a plus b to the power of 6 or 7, yes, we can just go on by we know a plus b whole square. In order to get a plus b whole cube, I do a plus b whole square times a plus b. But if I require the expansion of a plus b whole to the power of 5, and I only know a plus b whole square, then I'll be starting with a plus b whole square, getting a plus b whole to the power of 3, then a plus b whole to the power of 4, finally a plus b whole to the power of 5 by actual multiplication, which is really time consuming. So, we obviously will not be applying the direct multiplication technique when we have one alternative method with us. Okay. Now let us solve a question on this binomial expansion using the Pascal's triangle for getting the coefficient. Now they are saying there are two parts for this question. Find first subpart A says find the binomial expansion of 2 plus x to the power of 5. And subpart B says hence find the value of 2.01 to the power of 5. Okay, so let's start with our answer. Subpart A. Now we have learnt about A plus B to the power of n. And we are seeing the expression that is given to us is 2 plus x to the power of 5. Okay. So first thing that we have to understand is A and B are variables which can take any value. And of course, n is another variable. So for this question, for the question that has been given to us, the A value is equal to 2, the B value is equal to x, and the value of n is equal to 5. Okay. A is equal to 2, B is equal to x, and n is equal to 5. So we start with our Pascal's triangle. I had shown the Pascal's triangle right in the 5th row of the Pascal's triangle, but I am writing the Pascal's triangle again. I am drawing it. So this is the first row, this will be the second row, this is the third row, this is the fourth row, this is the fifth row. So we are interested in this fifth row because the power of the binomial expression is 5 or n is equal to 5. Okay. So we can, and we will be coming to plus and minus part, the sign between the two terms of the binomial expression can be a plus or a minus, but right now we only learn for the plus sign. Okay. So we know that there will be 5 plus 1, that is 6 terms in total. So let me just have 6 places, 1, 2, 3, 4, 5 and 6. Okay. Next, what we know? We know the coefficients. So let me just write the coefficients. 1, 5, 10, 10, 5, 1. And of course, the in-between signs will be plus. Okay, let me first of all write the terms and then I'll be putting the plus signs because I don't know how much space I'll be requiring. Next, it will be having a starting power equal to the value of n. So A should get raised to the power of 5 in the first term. And what is the value of A? It is 2. So times, obviously all the factors are getting multiplied. So it is 2 raised to the power of 5 because it should be A raised to the power of 5. N is equal to 5, so it should be A raised to the power of 5. And what is the value of A? It is 2. So 2 raised to the power of 5. And what will be the power of B? B's starting power is 0. So it is B is x. So x to the power of 0. Okay. And there is this plus sign in between. Next, the powers of A will go on decreasing by 1 and the powers of B will be going on increasing by 1. And A is 2. So it is 2 to the power of, this power is 5. So the power of 2 will be 4 in this term, and power of b, that is x, will be equal to 1, plus 10 times 2 to the power of 3 times x square, plus 2 to the power of, this is multiplication, 2 to the power of 2 times x cube, plus 2 to the power of 1 times x to the power of 4, plus 1 times 2 to the power of 0 times x to the power of 5. Okay. So this is equal to, x to the power of 0 is 1. So 2 to the power of 5 is 32, plus 2 to the power of 4 is 16, and 16 times 5 is 80. So 80x. X to the power of 1 is x. Next is 2 to the power of 3 is 8. 8 times 10 is 80. This time it is x squared, plus 2 to the power of 2 is 4 times 10 is 40, x cubed. 2 to the power of 1 is 2 times 5 is 10, x to the power of 4. And finally, 2 to the power of 0 is 1, 1 times 1 is 1 times x to the power of 5. Okay, so this is the expansion, this is the answer for our subpart A. Okay. Now coming to the subpart B, hence find the value of 2.01 to the power of 5. Okay. So 0.01. This is a single number, but we are dealing with binomial expression, so we have to split this number. We have to break this number into two parts. And those two parts should be connected by this plus sign. Okay. So how can we write 2.01? This can be thought of as 2 plus 0.01. Now we are having two terms connected by this plus sign. Okay. So 2.01 to the power of 5 can be thought of as 2 plus 0.01 to the power of 5. Okay. And what was our part A's binomial expression? It was 2 plus x. X is a variable. So x can be taking this value of 0.01. Okay. So 2 plus x whole to the power of 5 when x is equal to 0.01 is equal to 2 plus 0.01 whole to the power of 5. And we know what is the expansion for 2 plus x whole to the power of 5. Therefore, we will be just plugging in the value of x in this expression. X is equal to 0.01. Okay. So, this should be equal to 2 plus 0.01 to the power of 5 should be equal to 32 plus 80 times 0.01 plus 80 times 0.01 whole square plus 40 times 0.01 whole to the power of 3 plus, let let me write over here 10 times 0.01 whole to the power of 4 plus 0.01 whole to the power of 5. So this is equal to, for that we need the calculator. So it is 32 plus 80 times 0.01. 80 times 0.01 plus 80 times 0.01 whole square. 80 times 0.01 square plus 40 times 0.01 whole to the power of 3. 40 times 0.01 whole to the power of 3 plus 10 times 0.01 whole to the power of 4. 10 times 0.01 whole to the power of 4 plus 0.01 whole to the power of 5 plus 0.01 whole to the power of 5 equal to 32.808. So we can take it to be 32.8 approximately. Okay. So this is equal to, or I am writing over here, 32.8. Okay. So 2.01 to the power of 5 is approximately equal to 32.8 using the binomial expansion technique. Let us just try to get the value of 2.01 whole to the power of 5 directly using the calculator, and let us see what is the value of this. 2.01 raised to the power of 5. Sorry, missed the 2 part. 2.01 raised to the power of 5. It is 32.8. See, you are having exactly the same value. Okay. So that is the beauty of the binomial expansion. 2.01 to the power of 5, we can, of course, you may say that why should I be going for all these? You are having 6 terms over here, and I can directly get the value using the calculator. Definitely for this question it is a roundabout way to use the binomial expansion, but there may be times where this will be required. This technique will be required. Okay. So this was just for a practice. For if you are asked to get the value of 2.01 to the power of 5, definitely you will not be going for the binomial expansion, but this was just to make you familiar with this technique. Okay. So students, the video is getting longer, so let us stop over here for today, and we will be having one more session at least on Pascal's triangle, where we will be solving different questions, challenging questions on binomial expansions. So thank you for being with me till the end. Thank you for watching this video till the end. We meet again very soon. Till then, bye.